Here are the solutions to the Week 7 Check for Understanding. For this first problem, where I asked you to find the roots exactly, my apologies. I think I accidentally messed up one of the signs here, but this polynomial that I gave you does not have any friendly roots. What I had wanted you to practice was finding one friendly root, using it to divide, ending up with a quadratic that you could then use the quadratic formula on or factor to find the remaining roots. And I accidentally created a polynomial that has no friendly roots, so I apologize for that. But in problem number 2, you'll see the same procedure that I was hoping that you would practice in problem number 1. So problem number 2, I'd like to write this polynomial as the product of linear factors. So what I did is I took technology and I used this polynomial and found a friendly root. So one root of this polynomial is x is equal to 1. So what I'm going to do is I'm going to divide this polynomial by 1 to come up with a quadratic. I'm going to use synthetic division, and if I use synthetic division I have to be very careful because notice this is a cubic and I'm going to have to remember to insert a 0. So there's 4x cubes, there's no x squareds, negative 7x, and the constant is 3. Okay, so with synthetic division we'll multiply and then add, we'll multiply and then add, we'll multiply and then add. And I was expecting to get a 0 here because I knew that 1 was a root. So now I know that this factors as x minus 1 times 4x squared plus 4x minus 3. Now you can either go to the quadratic formula to factor, to see how the second term quadratic would factor, or you could just try factoring it. So I'm just going to see if it factors because I think it does. So let's break this up using a 3 and a 1. And yeah, let's just double check. 6x minus 2x is 4x. Yeah, our signs are great. So this is how it would factor. If you were looking for the roots, then you would just set these other two equal to 0. But this problem didn't ask us for all the roots. It just simply said, write it as a product of linear factors. Okay. Now let's take a look at this rational function. So find the domain. So for the domain of a rational function, just remember that the denominator cannot equal 0. And so when we look at this denominator, it's already factored for us. So we know the domain is going to be all real numbers, except there's 3 values that x cannot be. X cannot be negative 1, x cannot be 2, and x cannot be 5, because these are the values that would make the denominator equal to 0. Find all vertical asymptotes. A rational function has vertical asymptotes where the function is undefined. So a vertical asymptote would be the line x is equal to 1, x is equal to 2, and x is equal to 5. This rational function has 3 vertical asymptotes. Find all horizontal asymptotes. If we were to multiply the top together, the numerator, the lead coefficient would start with a 2x squared. And if you were to multiply the denominator together, the first term would start off with an x cubed. And so to find the horizontal asymptote, an easy way to do that is to take the ratio of the leading terms, so that would be 2 over x, and ask what happens as x gets really large. So as x approaches infinity, 2 over x approaches 0. So we know that this rational function is going to have a horizontal asymptote at y is equal to 0. In other words, the x-axis is a horizontal asymptote. Discuss the behavior of f of x at the vertical asymptotes using arrow notation. All right, one of the ways to do that is just to simply graph the rational function using technology, which is what I did. And if you do that, you'll find out that as x approaches negative 1 from the left, f of x approaches infinity. And as x approaches negative 1 from the right, the function approaches negative infinity. At the next asymptote, as x approaches 1 from the left, f of x approaches infinity. And as x approaches 1 from the right, f of x approaches negative infinity. So that's the behavior at this asymptote. Oops, this is actually a 2, the other asymptote. And this asymptote. And finally, let's talk about the last asymptote. Okay, so at the last asymptote, as x approaches 5 from the left, the function approaches negative infinity, and as x approaches 5 from the right, the function approaches infinity. Find the x and y intercepts of the function. So the x-intercept is going to be where f of x is equal to 0. And a function is equal to, a rational function is equal to 0 where the numerator equals 0. And so if we look at the numerator of this function and ask ourselves, when is it equal to 0? The numerator is 2x minus 1 times x plus 2. And this is equal to 0 where x is equal to 1/2 and where x is equal to negative 2. So these are the x-intercepts. We can write them in point or as ordered pairs, 1/2 comma 0 and negative 2 comma 0. And finally, find the y-intercepts. The y-intercepts, let's see where we can squish that. Let me try to squish it over here. The y-intercept, to find the y-intercept, you need to find out what f of 0 is. So if we take our function and we plug in a 0 for x, so everywhere we see an x, we replace that with 0, we're going to have negative 1 times 2 divided by 1 times negative 2 times negative 5. And again, we're getting that by simply putting a 0 in for x. And if we do that, we're going to get negative 2 over negative 10, or in other words, 2/10 or 1/5. So the y-intercept would be the point 0, 1/5. And finally, give an example of a function that has a slant asymptote. How do you know your function has a slant asymptote? So a function, a rational function, is going to have a slant asymptote anytime the degree of the numerator is exactly 1 more than the degree of the denominator. So if you want to check that your answer is correct, simply look at the degrees of your numerator and denominator. So for example, here's a function. F of x is equal to x cubed plus 7 over x squared plus 3x minus 1. This would be an example of a function that has a slant asymptote because if we look at the dominant terms, the degree of the numerator is exactly 1 more than the degree of the denominator. And that's the solutions for this week's problem set.